Welcome friends. Today we will discuss we will discuss about real gases. Okay. Yesterday class we uh, discuss some things under the ideal gas. Okay. What is ideal gas and what is the assumptions of ideal gas and laws of the ideal gas, Charles law and Boyle's law, and equation of state of ideal gas, which is PV equal to RT. Those things are all under the ideal gas concept. Okay. Okay, ideal gas. But in real gas, what is real gas? Okay, the ideal gas equation of state PV equal to RT can be used with the assumption of very little or no attraction forces of molecules within the gases, and the volume of molecules is negligibly small in comparison to volume of gas, which is volume occupied by the particular quantity of gas is nothing but the volume occupied by a particular volume, but the number of molecules available in that particular volume is different. This is the concept of gases. Okay, the gases doesn't have a definite volume, it occupies its whole volume, a whole volume of a container. Okay, then in ideal gas, the volume of a particular molecule is negligible one. We have considered only overall volume of a container. Okay, sir, volume. Okay, please consider. But in real gas, the gas having molecule, the molecule having some finite volume, and the in between the molecules having small attraction forces also available. These things are is for the real gases. Okay, then for many gases at a very low pressure and high temperature, the forces of intermolecular attraction and volume of molecules compared to the volume of gas are significantly small, and real gases obey very closely the ideal gas. But at higher pressure, the forces of intermolecular attraction and repulsion are significant, and volume of molecules are also appreciable compared to total gas volume. Then the real gas behavior deviates from ideal gas behavior. A slight modification in the ideal gas equation of state to fit real gas behavior is to introduce a correction factor called compressibility factor. It is defined as is Z equal to PV by RT. This is the notes from book. Explain. At very low pressure, all gases approach ideal gas behavior. At very low pressure means atmospheric pressure, ideal gas and real gas both are same. Both are obeys PV equal to RT. But at higher pressure, the volume of the molecules is a major contribution of volume of the whole container. Okay, at the particular situation, the gases is considered as a solid or liquid, which means in the solid and liquid, the intermolecular forces are exist. In similar manner, at higher pressure, the in between the gases also, gas molecules also having same molecular attraction forces. Therefore, that forces is deviates from the ideal gas and to real gas. Okay, then see the diagram. Real gas is going approach to pressure del P, not a P, delta P, change in pressure at lower pressure is P tends to 0 and it is equal to ideal gas. Okay, then to define that real behavior in the mathematical formulation, that I introduce one factor which is compressibility factor. Okay, compressibility, the word means compression. Okay, then the Z equal to PV by RT, which is nothing but PV equal to mRT. Sorry. PV equal to small v, okay, RT is the equation of state for a ideal gas. Okay, but in real situation, PV not equal to RT. Okay, this means that volume, the overall volume occupied by the gas is not similar in ideal and real gas, because in real gas the molecules having certain small amount of volume. Okay, that volume is must be subtracted from the total volume. That subtracted volume is only for a volume occupied by the particular container. Okay, remaining volume. Therefore, that deviation, which means, for example, the volume of the each molecule consider B, then P into V minus B equal to RT. Okay, these things are right. Right. So, in real gas situation, PV doesn't equal to RT. Therefore, I introduce some compensation factor. Which is equal to Z equal to PV by RT. For ideal gas, that Z equal to 1, which means PV equal to RT. Okay, but in real gas, that compressibility factor is maybe greater than or less than that, based on the property of the gas. Okay, for real gas, is a function of pressure and temperature, and it's usually determined empirically. It's not an exact value, it is an empirical value. Empirical value means an assumed value. Okay, repeated experimentation. From that experimentation, we have derived or solved an empirical equation. With the help of that empirical equation, we have determined the values. This value is called empirical values. Okay, the real gas behave differently at a given temperature and pressure, but they behave very likely at their reduced pressure and reduced temperature. Okay, the real gas behave differently at a given temperature and pressure. Okay, real gas is based on the different temperature and pressure, but an ideal gas doesn't change temperature and pressure, but in real gas behave differently with the temperature and pressure. What is reduced pressure? Here the book says word that reduced pressure. Reduced pressure is nothing but PR equal to P actual divided by P critical. P actual means current pressure. P critical means critical pressure of a particular substance. Critical pressure of a particular substance. All substance having that critical pressure. Okay, for liquid, for water, the critical pressure is 220 bar. This type of values for each and every substance in the water. Okay, critical means the maximum phase change temperature. The maximum phase change temperature, which is called critical temperature. Okay, in every substance having one critical temperature. Okay, beyond that temperature, the phase is not identifiable. What type of phase that substance having at the particular instant, it's not identifiable. Okay, beyond the critical pressure. Below the critical pressure, only that substance, either solid or liquid or gas, that classifications are there. Beyond that critical pressure, there is no classification. Okay, it's a plasma state. Okay, ionic state, called as a ionic state. Okay, that pressure is called critical pressure. At that temperature is called critical temperature. At that volume is critical volume. Okay, and actually is current pressure measured, current pressure and current temperature. What type of experiment we have done and particular time what type of pressure is there. This values are called actual. Okay, therefore from that we have calculated the reduced pressure. These reduced pressure are mostly common for all gases. Okay, then PR P actual by P critical and TR T actual by T critical, and VR is V critical by V actual by V critical. Then the disadvantage of the use of compressibility factor chart is that a separate chart is needed for each gas. Separate chart, because every gas behave very differently with pressure and temperature. Each gas, okay, all gases behave in same manner for different temperature and different pressure. It's not a correct. Each and every gas behave differently with different temperature and different pressure. Okay, therefore we have draw the compressibility factor chart. The chart is for we must draw the chart for every gases. It is a very difficult. Okay, but the same reduced coordinates. Okay, reduced pressure. The compressibility factor is approximately same for all gases. Okay, but with the help of reduced coordinates, the compressibility factor is approximately same for all gases. It's called law of corresponding states. The main important word, law of corresponding state, which is every gas in the world behaves differently with different pressure and different temperature. Okay, therefore we cannot draw the compressibility factor chart for each and every gas. It's also very difficult. Okay, therefore we have used the reduced properties. That reduced property, the Z value is moreover same for different temperature and different pressure for all gases. Okay, this statement is called law of corresponding states. Okay, this VR equal to function of PR and TR. Okay, then a diagram of PR versus TR as parameter plotted from data of any gas would apply to all other gases, a generalized compressibility chart. Okay, and PR versus TR, we have plot a graph. That graph is called compressibility chart. Okay, here Z values are plotted against PR and TR for several gases. Okay, Z value are plotted against PR and the constants are TR for several values. Okay, I explained the diagram. The compressibility chart is a very useful chart for all determine the properties of all real gases, which is very useful. The compressibility chart is this. Here is PR, reduced pressure, is reduced temperature, and is compressibility factor. With the help of PR and TR, we have find the Z value. The Z value varies from 0.1 near 0 to 1.1. The maximum value is 1.1, but that value is not reached. The compressibility factor may be greater than 1, and most of these cases the compressibility factor is less than 1. Okay, see the diagram. But in nitrogen at TR equal to 2, TR means T temperature, T actual divided by T critical. The ratio is TR. At 2 TR, the nitrogen having the compressibility factor is greater than 1, which means PV is less than RT. Okay, and remaining situation, that Z value is always less than 1 for all gases and particular PR and TR. Okay, TR value increases from 1 to 1.10, 1.20. This type, this manner, the TR value is increased and PR values are increased in a horizontal manner. With the help of these two things, we have determined the Z value. Once we determine the Z value, then we have calculated the PV, substitute the PV Z as PV equal to ZRT equation, then determine the same, proceed the same calculation and find out the unknown parameters. Okay, this is the use of generalized compressibility chart, okay, for various cases. In that, see the curve. In that curve, all gases which are cross for methane and circle for ethylene and light triangle for ethane, this type of gases are plotted. In all gases having same property for a particular TR and particular PR. Okay, therefore this is the use of reduced pressure and reduced temperature. Okay, then the very important graph, okay, which is called compressibility chart. Okay, these are the real gas equation of state. First one I said PV equal to RT, which is the ideal gas equation of state, and another one is which is the real gas equation of state. It is from Z is I introduced one term which is Z. Z is called compressibility factor. That compressibility factor is calculated empirically only. Therefore, it have some errors, which means that factor having some errors. The chart also having some errors. Okay, then another type of equation of states. PV equal to RT is one type of equation of state, and PV equal to ZRT is another type of equation of state. But in that Z is calculated empirically, at a exact equations. The Z having a not exact equation. That Z is determined from the compressibility chart alone. Okay, otherwise that chart also having some errors. Okay, then now we discussed another type of some equation of state for a real gases to to get a accurate results. Okay, that equation of states are, first one is van der Waals equation of state. This equation of state already you know, van der Waals equation of state. That equation of state is having three constants, P plus A by V square. A is one constant and B is another constant and RU is another constant. Okay, that RU is a universal gas constant and B is one type of constant and A is another type of constant. These constants are derived from that reduced properties for a particular gases. A is equal to 0.0427 into RU universal gas constant and TC reduced critical temperature and PC critical pressure, and TC is TR is reduced, TC is critical. Okay, A is calculated with the help of TC and PC, B is calculated with the help of TC and PC for a particular gas. Okay, this is one type of equation of state. I didn't explain the derivations. Okay, this is not our scope. It is a scope of ME subject, which is called advanced thermodynamics. Okay, that so I explained only that what is equation, what are the constants available in the equation. Okay, that's only the scope of our subject. Okay, then second, Redlich-Kwong equation. Okay, in Redlich-Kwong presented an equation of state two constants. Okay, two constants. In that equation, we have two constants. Okay, then third, Beatty-Bridgman equation. equation of state, the measured values of pressure, temperature and specific quality with good accuracy. Okay, in that equation they substitute three constants a, b, c. A and b and c. A equal to a naught 1 by ab, b equal to b naught 1 by bb. These are the constant terms. Okay, these equations of state which is used to determine the properties of particular gases, real gases, the accurate manner. Okay, this only. Therefore, in different years and different scientists and express their views in the form of equations. Okay, if you interest on the topic, you also derive a different type of equation of state and prove that equation of state, and you can also present that equation of state in the value. Okay, then fourth, Benedict Webb Rubin equation of state. Here the Benedict Webb Rubin equation of state, that Benedict introduced 8 constant equations. Okay, the equation having 8 constants. Those are a naught, a, b naught, b, c into 10 to the power 4. Sorry, it did become equation of state constants. Then Benedict equations a naught, b, b naught, c, c naught, alpha, comma. That equation is the equation of state. The equation for the state is this. This is for PV, alternate equation for PV equal to R. See that equation. This is the difficulty of equation, because in realistic situation is very difficult. Ideal we can assume anything, but in real we have define each and every steps and components. Therefore, that equation becomes very difficult. Remember, PV equal to RT is the equation of state for ideal gas, but Benedict introduced the equation of state for real gas is like this. That equation having 8 constants. With the help of this 8 constant, we have find out the properties. Okay, this is the difference between real and ideal gases. Okay, then the constants are B naught, A naught. These values are different from each components. When substitute the components, we can measure the pressure, temperature, and volume of the particular instrument. Okay, then last equation of state is Wirral equation of state. So Wirral equation of state, which is a series. It's not a limited equation, not a fixed equation. That Wirral equation of state is a series one, which is PV by RT equal to 1 plus A by V plus B by V square plus E by V cube plus T by V power 4 plus E by V power 5, etc. etc. A series. It's not a fixed equation. It is a series. Okay, please understand. It's a series. Then how much term we have need? Up to the term we add the constants. Okay, this is Wirral coefficients, called Wirral coefficients. Okay, these are the other equations of state to define the real gases. Okay, first one is PV equal to ZRT, or Z equal to PV by RT. With the help of compressibility factor, that compressibility factor is determined by the chart. That chart also having different errors, but that calculation is very easy. But the other equation of state, with the help of other equation of state, we have measured we have calculated the accurate value, but the equation is very difficult to understand, because the equation is having too many numbers of constants. Okay, that every constant is different for every component and every temperature situation. Yeah, that is a difficult, but introduce some equation of state to measure the property of the particular substance accurately. Okay, those things are only we discussed. Okay, first one is ideal gas equation of state, and another is compressibility factor, and next other equation of states are Wirral, Benedict, RK equation, and Van der Waals equation. This type of equation of states are available. Okay, Thank you. Tomorrow we discussed a mixture, properties of gas mixtures. Okay, Dalton's law of partial pressure and partial volume, this type of things are discussed in tomorrow classes. Okay, thank you.